Okay, so the question that you asked was related to just the partial derivatives. So the setup with if we're using Lagrange multipliers method means we need to find our capital Y, which would be taking your function you're trying to min or max, and then adding, or the book subtracts, but it's the same thing, lambda. It's the world's worst lambda. Let's fix that. Lambda times your constraint set equal to 0. So your constraint would just end up being 0 equals 12 minus x squared minus y. Or, vice versa, you could have done y minus 12 plus x squared equals 0. It doesn't matter. That's why this here can be plus or minus, because there's no way to control which way you're going to make this thing equal to 0. It's this equivalent of just multiplying through by a negative. So again, it really doesn't matter. I'll just go with this one over here. So it's 12 minus x squared minus y. So now the partials. So some people, until you get stronger with your partials, you may want to distribute this lambda through. I personally do not, but I will do it for the student out there who may need it. So that's 12 lambda minus x squared lambda minus y lambda. So now when I take my partials, the partial with respect to x, okay, well, so the first term has an x in it, so we're going to take the derivative. So it's x to the first, so the 1 comes out to the front, making it 1, x to the 0, y. But as we all know, anything to the 0, that is just 1. So that leaves us with 1y, so 1 times y is just y. Okay, so that term right there is just y. So then here, this next term, there are no x's, so the derivative of that would be 0. The next term here, there are x's, so we take the derivative of that like normal. So the 2 comes down to the front. So that raises x to the 2 minus 1, that makes 1. The lambda is going to stick around because it's a constant. So we just don't need to write the 1 exponent. And then the last term, there's no x's, so that would be 0. So again, we don't need a whole bunch of this. So simplifying this would just leave us with y minus 2x lambda, or 2 lambda x. Doesn't, technically the x is the variable and the lambda is a dummy variable, so we'll write it like that. Okay, so there's the partial with respect to x. Now we repeat. Now we rinse and repeat. Now we do the partial with respect to y. And then we're going to do it again with lambda, but y. There we go. So the partial with respect to y, well, so for our first term, again, we have a y, so the derivative of that, the 1 comes to the front. So that leaves us with x times y to 0, but anything with 0 is 1. The next term, no y's, so 0. Next term, no y's, so 0. Next term has a y, so we're just going to end up with minus lambda. Then, last but not least, the partial derivative of f with respect to lambda. First term, no lambdas. Second term, lambda, so this is with 12, because the derivative of the lambda is to the first, the 1 comes to the front, raises to 0. Okay. So here lambda, so it leaves us with x squared minus y. Notice, this matches our constraint. It always does, so you don't even have to really think about that derivative when you're doing it. Just whatever you had up here, that just pops right down to there. So now we're solving a system of equations. And it seems like here is where your question stops, so I will stop there as well. But just I will give you my tip. I always recommend solve one of these equations for lambda, because it's the variable we don't care about at this point. It actually does have a lot of meaning, but in this class we're not going to worry about it. So we're going to set each of these partials equal to 0, solve for lambda. So therefore we end up getting lambda equals x. Now use substitution technique. Everywhere you have a lambda, sub it in, and now the solving becomes relatively painless, or not painless, but easier, because now we're going to end up with lambda of x times x, or aka that's just x squared, so I will write it as x squared. So now when I'm solving this, I have one system of one equation that has x's and y's. Then if you compare that to over here, now I have another equation that has just x's and y's. So I'm going to put these two together and solve another system. So I've got 0 equals y minus 2x squared, and the second equation is 0 equals 12, what was it, minus x squared minus y. So now this just goes back to solving systems like we had before. You could substitution technique, an elimination technique. Since these aren't linear, you be careful. Would be relatively easy just to solve this for y, sub it in. Anyway, I hope that's enough. Let me know if you need any more.